The broadcast is now starting. All attendees are in listen-only mode.
Hey everybody, welcome back to Young Engineers of Today. I hope you had a good week so far. I hope you're ready to continue with more Fly to Learn. So as I understand it, you guys have gone through most of Lesson 12. You've actually designed your own plane and flown it, and now we're ready to move on. But first, we're going to start it off with a challenge, and I'm going to give you guys about 30 minutes to work on this challenge. We're going to design a sport plane with the following requirements. You want it to have 2 passengers, including the pilot, 250 thrust horsepower, and an aspect ratio between 6 to 8. So just as a real quick refresher, 2 passengers, including the pilot. We went over how to calculate the weight of the plane, which is just, the average passenger weight we can run with 170 pounds, and we'll assume that they're going to carry 20 pounds of luggage. I don't know why you wouldn't a sport plane, but hey, whatever. So let's say 190 pounds per person. And so calculate the passenger weight based on that, and then you can calculate the gross airplane weight. Remember, that's the total payload weight divided by 30%. So that's going to be however much our passengers weigh combined times 0.3 in order to get the gross airplane weight. Then from there, you can get the standard wing loading. And then the standard wing loading can give you the wing load range, as well as the wing area. The wing area can give you the wingspan and the chord. And then the horsepower, you can calculate the rated horsepower and the thrust horsepower and everything like that. And then get the fuel and everything. So what I challenge you guys to come up with is basically fill out these fields here with those starting requirements. And I'll give you guys about half an hour to do it. If you have any questions about anything, feel free to let me know, and we can walk through it. Otherwise, we'll at about 8:30 we'll review how to do that, and then design an airplane for it, and then we can try moving on to gliding. In the meantime, my cat is going to yell at me. Alrighty, just a couple more minutes, and then we'll wrap up with the challenge and go over how to do it. Alrighty, so let's spend some time going over this. So, 2 passengers, including the pilot. Let's pull up a notepad here so we can take some notes. Let's not click away from it. Here we go. We've got our calculator. So we want 2 passengers, 250 horsepower, thrust horsepower. Let's make that distinction. And an aspect ratio from 6 to 8. So what all does that entail? So the average weight of each passenger plus luggage, let's assume that there's luggage. So the average weight of each passenger per passenger is going to be 190 pounds. So passenger weight, or let's call it payload weight is going to be 190 times 2 because we got 2 passengers, right? So 380. Our gross weight is what we're going to determine next. Gross weight is going to be the total payload weight divided by 30%. So if we take 380 here, which is going to be our payload weight, and divide it by 0.3, so 380 divided by 0.3, that's going to give us a total airplane weight, or a gross weight, of 1,266. Let's say 1,267 pounds. So that's going to be how much our airplane is going to weigh with passengers and fuel and just generally existing. Once we've gotten that, we need to calculate the size of the wings. So our standard wing loading is going to be the weight divided by the surface area, or 2.24 times the cube root of the gross weight minus 6. So if we take the cube root of the gross weights, we get 10.81. Then let's subtract 6 from it, and then we'll multiply that times 2.24. So our standard wing loading is going to be 10.8 pounds per square foot. We don't really need to calculate the high or low wing loading range just because we don't care. So we've got the wing area by calculating the gross airplane weight divided by the wing loading, and we'll keep it on standard. So 1267 divided by 10.8 gives us a wing area of 117.3 square feet. Cool, we're getting somewhere. So now we want an aspect ratio between 6 to 8. Why don't we keep it at 7? We'll just split the difference, make it easy. So we got an aspect ratio of 7. We got a wing area of 117.3 square feet. In order to get the wingspan, we take the wing area and we multiply it by the aspect ratio and then take the square root of it. So 117.3 times the aspect ratio, and then we take the square root of that, which gives us a wingspan of 28.7 feet. And then the chord is simply the wingspan, or excuse me, the wing area divided by the wingspan. So we take 117.3 and divide it by 28.7, which gives us a chord of 4.0, well, let's do 4.1 feet. So we've got a width of 4.1 feet and a length of 28.7 feet. Our wings aren't very big, but then again, our plane isn't supposed to be very big either. So we've got our thrust horsepower of 250. If we divide that by 0.8, so if we take 250 divided by 0.8, we've got a brake horsepower of 312.5 horsepower. And if we take our 250 horsepower and we multiply it by 0.75, our rated horsepower is going to be 187.5 horsepower. So that's us being able to run the plane at 75%. That's our cruising horsepower. So now let's see how far we can fly our airplane on a tank of fuel. If we've got our gross airplane weight of 1,267 pounds, and we multiply it by 0.15, because again, another rule of thumb, we get a fuel weight of 190.1 pounds. So we carry 190 pounds of fuel generally. If the payload weight is 380 pounds, payload weight is 380 pounds, then our empty weight is 190 plus 380, 570.1, so 1267 minus 570.1. Our empty weight, with no fuel and no people in it, is 697 pounds. Or, well, let's keep the same, 696.9 pounds. There we go. So our cruise speed is, we didn't actually get a cruise speed. Yeah, we didn't actually get a cruise speed. Well, that makes things a little bit more difficult, doesn't it? Well, so we can't calculate the range. Or, anyway, yeah, we can't calculate the range, but we've got at least the rated horsepower, we've got the chord, we've got the wingspan, we've got the empty weight, the fuel weight, and the gross weight, so that you would be able to actually input this plane into the plane design for X-plane. And generate a sport plane that you could then try and fly. So next, we've got gliding. I realize that we're not actually going to build the plane right now. I'm not going to go through the process of building the plane. We could just move on to the next lesson. So the earliest form of unpowered fixed-wing aircraft were known as gliders, which were inspired by the flight of birds. Early aerospace engineers used gliders to gain an understanding of aerodynamics. So glider design relies on many of the same principles as aircraft design, but must be slightly altered to account for the lack of propulsion. You want to minimize weight, drag, or you want to minimize weight and drag, and you want to maximize lift. Always with gliders. You want smooth, curved edges to improve aerodynamics, since both parasite drag and induced drag decrease the efficiency of the glider. And the glider can't produce thrust to overcome this drag. Gliders also utilize the same control surfaces as aircraft, so what makes them so different from planes? So other than the obvious lack of propulsion, gliders are different from planes in the following ways. Gliders have an increased aspect ratio. The wingspan of gliders is much longer in order to increase the lift they generate, as well as decrease the effects of lift-induced drag. In response, gliders have a higher maximum lift-to-drag ratio. However, there are structural limits to the length of the wingspan. If they are too long, the glider's wings may buckle. Gliders are more general purpose. While aircraft have a variety of uses, they are mostly used for travel. Since gliders fly without power, they're not suited for rapid travel. They're most often used to acquaint new pilots with aircraft controls, or sightseeing, or for novelty. Ballasts. Because gliders are so light, the center of gravity may easily be changed with undesirable consequences. Some gliders use a weight called a ballast, which can be added to shift the plane's center of gravity and allow them to fly. And then you got methods of increasing altitude. Gliders must be towed by a powered aircraft or launched off a high surface to achieve flight. Additionally, they are only able to greatly increase their altitude by using atmospheric phenomena known as thermal convection currents. These are currents of hot air that rise straight up into the atmosphere. These are actually the same things that birds use in order to minimize the energy needed in order to stay aloft. So you hit one of these things and you sort of get pushed upwards and you got a greater altitude, and then you can fly a little bit longer. All airplanes can function as gliders if their engines are turned off. However, powered airplanes are not nearly as efficient as gliders in their ability to stay aloft. Powered airplanes really depend upon their ability to be powered in order to stay in the air. So if they can't, then they don't fly nearly as well as gliders do. So gliding performance is measured by a quantity known as the glide ratio. A glide ratio of 30:1 means that it can travel for 30 meters horizontally while only falling 1 meter. Most gliders today have a ratio of 50:1 as compared to the 15:1 ratio of most jet aircrafts flying today. So that is to say, most jet aircrafts can glide 15 meters for every 1 meter they drop in altitude. Gliders can fly 50 meters for every 1 meter they drop in altitude, which is much, much more efficient. Powered aircraft also descend more quickly than gliders due to their higher weight and consequently their higher wing loading. So knowing that drag is wing loading times the sine theta, and lift is the wing loading times the cosine theta, we can find the relationship between glide angle and lift and drag ratio. The angle theta being, I think in this case, if we were to draw, so we've got our plane here, right? Our plane being all planey and stuff. Let me make it look more glidery. So we got our glider here doing its glider thing. So for every 50 meters it drops 1 meter. And this can be expressed as a triangle because you got that line there. And then we've got an angle theta here, which is the angle of this part of the triangle. So that angle theta can be used here. So we can find the relationship between glide angle and lift and drag ratio as tangent of theta is equal to 1 over lift divided by drag. So now we're going to find the glide angle and the glide ratio for the Cessna 172 using X-plane. Oh boy. Okay, yeah, so let's go ahead and get X-plane all opened up. I'll go ahead and close down the plane maker since we're not really going to be running with that. Run the demo. Ultra realistic flight simulation. All right, so we'll do our basic Cessna. X-planes, no. General aviation. There we go. Cessna 172 SP, and it's going to be KSEA Seattle Tacoma. Day and clear. I'm going to hit fly with these options and let it load. So these are just the default options that we've done for all of our experimental flying in the past, provided we haven't been designing a plane and trying to fly that one. We wait patiently for X-plane to start up. We wait as X-plane tests the limits of our patience. We may not, in fact, be able to. Oh, let's see here. Reading scenery files. I do have a lot of things open, it's true. Let's see here. Get out of here. No. Finishing asynchronous loading. I am not entirely convinced that that was a result of me closing that program. I think that just happened to be coincidental, but that was certainly quite the coincidence. Now it's going to load planes into memory that aren't being used. Okay, here we go. Boop, pause. So what we want to do here is we're going to start 3 nautical miles away from runway 16. Then we're going to look at the latitude, longitude, and altitude, location, velocity, and distance traveled, and liftover drag and coefficients. So go up here to settings, data input and output, uncheck speeds. So we're going to keep location, velocity, and distance travel, which is 21. Undo landing gear deployments. Location, latitude, longitude, and altitude. And liftover drag and coefficients. So we've got 20, 21, and 68 all checked on the last two checkboxes. So we got what we need here. And then location. Oh, wait, no, excuse me. Quick flight, nope. Go back to my previous slide. Local, nope. Here we go. All right, so 3 nautical miles away from runway 16. I'm assuming 16L. So we'll hit that. And then it's going to reload everything. Good. All right, and we start out paused. Fantastic. And then from here, they're going to pull off on the throttle entirely in order to turn it all the way off. So it's no longer running. We're going to keep the orientation ball as level as we possibly can. Can't remember the name of it, so I'm going to call it the orientation ball. And we're just going to keep it as level as possible and descend as level as we possibly can. Using the final distance traveled and your starting altitude, you can now find the glide ratio. So we're just gonna travel until we hit the ground. I mean, gently, obviously. Yeah, thanks. Well, that's totally gonna mess with our operation there. All right, so at this point, you just glide. That's all we're doing here. Just gliding. And you just keep the gimbal down here level. Make any small corrections in case it decides it wants to go all wacky. We started at about 1,200 meters, I believe. Really should have kept track of that one. There, now the engine isn't running at all. Unfortunately, we don't know if we're level anymore because the low vacuum. All right, so, well, we're doing the best we can. And after drifting gently to the ground, keep track of how much we traveled. So, went through that. All right, about 15,000 feet, and then crashed wonderfully. 15,000 feet, starting at about 1,200 feet. You get an idea of basically what you're supposed to be doing with this experiment is just figuring out the ratio of horizontal travel to vertical travel, because if you can do that, then you can figure out exactly exactly what your glide ratio is. Anyway, that's gonna do it for today. So I'm gonna go ahead and ask the poll questions. Then you can spend some time experimenting if you'd like, or we can do question and answer time. Or if you've got stuff you got to do, you can head out, and then you can just enjoy the rest of your night and have a great weekend. And then we'll see you on Monday. There is lab on Thursday and Saturday. Just keep in mind. But yeah, we'll go ahead and do the poll questions and then leave it open for question and answer time like we always do.